can end a cycle of perpetuating mistakes over and over the project analysis. So that's the idea of the presentation. I'll bring some concepts first, and then I'll show some cases that we apply the simulation to show how we've been approaching this kind of problem with this very powerful tool. Before discussing the technical mechanics of a simulation, I would like to provide a brief presentation of Graf Infra Consulting, where I work. We are independent strategic and technical advisors, specialized not only in high precision multidisciplinary engineering. We do engineering projects from conceptual designs to executive projects. We do projects in any stage of infrastructure project, but we also are strategic consultancy and regulatory advisors. So we have this broad spectrum of operation. It qualifies us to help our clients on any stage of the project, from the initial conceptual design and feasible analysis to the go live of infrastructure assets. We've been working worldwide in many countries, and we have projects in the whole Brazilian territory. And over the last 3 years, since we were born, we delivered more than 100 projects in the infrastructure sector, many of them including simulation analysis. So let's jump to the subject of this presentation. When we analyze port development, a common mistake, a common risk that usually we see comes from inherited premises. It's frequent to adopt deterministic data from initial master plans or former studies. And usually this information, these premises, these assumptions are static data, static information. For example, we see a lot of studies using berth occupancy as a fixed average of 60%, 65%, whatever, or gate arrivals on a port terminal being treated as a perfect linear operation. But usually these phenomena, these processes, they do not occur, they do not happen with this precision. Usually on the real life, you have a lot of variabilities, a lot of randomness in this kind of process, and that's what simulation try to bring to the analysis. So when we build an infrastructure based on these unverified static means or inherited data from other projects or from magic numbers that the market uses, we face the risk of over or under designing the assets, which can lead to poor asset utilization or unexpected operation frictions down the line. So dynamic simulation is applied to address this specific exposure. So what is simulation, and when does it apply? The computational simulation is defined as a mathematical and logical replication of a real-world system behavior inside a computer model. So this is the first misunderstanding of what is simulation that we see a lot in the market. When we develop a simulation model, we do not try to replicate the exact real world with all its details in the computer. That would be virtually impossible. What we try to do is to assemble a simplified and representative version of the system that we want to study on a computer environment. So sometimes we don't need to model or to develop the simulation for the whole operation, but just for some specific processes inside the operation that we want to study. And it's important to understand that we do not try to replicate the exact real world. We try to replicate on a simplified version of the real world that is representative of what we want to study. So the idea is to create this kind of a digital twin and analyze the behavior of the system under volatile or random conditions before we invest or before we develop the physical asset itself. So it's a way to test our hypothesis before we spend a significant amount of money and then discover that the project was not the best solution for the operation. So the simulation is mainly useful when operation network shows three main characteristics. The first one is unpredictable variability. Actually, when we say unpredictable, we mean that it's not totally unpredictable or not total random variability, but we have some variability. So when we adopt static information like means, we don't get this variability. You don't get the worst case scenario or the best case scenario, and we cannot understand how the system will behave under these variable conditions. The second characteristic is component interdependence, which means when the behavior of one element or one link of the process affects the behavior of several others. So here we are talking about complex systems that they are usually not linear. So the behavior of one element affects more than just the next element of the system. And the third condition, the third characteristics is when you're talking about complex operational rules. So again, it's not a linear system. You have operational options. You have different operational conditions, and it's hard to understand the result of all these several conditions with a deterministic model, with a fixed static model. So this is when we use simulation to help understand the project. So when we talk about unpredictable variability or randomness, we talk about like weather windows that might change, supply chain delays, equipment breakdowns, all this kind of variability that we do not control, but we can predict, and how they affect each other. So when you assemble a simulation model and you have several steps on your process, several links of your process, and each one of them has a variable behavior, the way they affect the other stages of the process can vary according to the result of that first element. So you don't get one result for that analysis. You get a range of results, and that's the difference from the simulation approach of a deterministic approach. So it's important to define the scope and the limitations of this technology, this approach for the proper deployment of a simulation. So simulation basically functions as a decision support mechanism designed to resolve specific what-if operational questions. So it's not optimization tool. It's a different tool. A lot of people make some confusion about that. So the idea of the simulation is to replicate a system on a computer environment and test hypotheses. So what if I do that instead of this? What if I do this instead of that? And this is the main use of simulation. So it serves as a tool to test capacity alternative, to try to discover unhidden dependencies. This is very common to happen when you are designing a simulation model. You find out that some specific process of your system affect other stages of your system in a way that you didn't expect. So this is very common, and it helps to validate the solution that is being proposed. So it's not an automated optimization algorithm. It's a different approach. Optimization is when you try to enhance or to increase some of the characteristics of the model. And in simulation, we don't do that. We just uh, test different hypotheses and see and try to understand how the system behave under variable conditions. The simulation cycle is not a linear cycle as it is shown here. So it doesn't start here and I'm sorry. It doesn't start here at the problem formulation and end up here. Actually, it does, but it's like a cycle. So you can go back and forth during the development of the model. So it's not just linear. But developing a reliable model requires this iterative approach. The process begins with the problem formulation, is where you define what you want to answer, what is the objective, what is the focus of the model. So again, we are not trying to replicate the reality with all each details on a computer environment. We are trying to design a computer model that explain or represent a specific condition or specific system, uh, just on the enough detail to answer the questions that we want to address. So it's not, we don't build a model and then see what we do with that. We first formulate the questions that we want to answer, and then we build a model with that objective. So this is something very common to happen when we are developing a study for a client, that at the middle of the process, the client comes up with different questions or different problems that the model was not designed to answer. And this is not a problem with the model, but this is a problem with the initial formulation of the solution. So we spend a lot of time in this stage of the project to understand exactly all the answers that the client wants, and all the analysis that he might be wanted to do in the future, so we can build the model that will help during the decision process. After we define the problem that we want to address, we we design a conceptual model. So here we are not talking about software yet. We do like a system flow, or we sometimes we do on hand, on paper, and we design what we are going to build, to assemble on the computational model. And based on that, we define the information that we need, the data that we need to collect to fit the model. So uh, we don't need to get all the information about the operation, just the information that we need to fit the specific model that we are building. After that, we validate the conceptual model with the clients, all the inputs that we are going to need, all the outputs that the model we're going to bring, and if these outputs will answer the questions, then we go to the verification and validation. Here we build the computational model itself. It involves sometimes operation, coding, sometimes spreadsheets, whatever tool that you are using, and we do the validation. So we try to replicate the real behavior of a real system. So if we are designing a simulation model for a specific port terminal, we get historical data from the port. We feed our simulation model, and we try to see if the outputs represent the reality. When we get this validation, we have some we can be sure that the model will answer the questions that we want to address on a proper way. So we validate the model as with the operation as is, and then we go to the hypothesis testing, which is the last step of the construction process. It's a experimentation and decision support. So after we have a model validated, we can do the hypothesis, the what if questions, and we can add resources, add demand, or whatever that we need to do to get the answers and the support to the decisions that we have to go through. So one of the main benefits of the simulation approach comes from this contrast between deterministic and stochastic modeling. Deterministic is when you use fixed assumptions. You use fixed data, so your inputs are always the same. Obviously, your output will be the same. And stochastic modeling is when we consider some randomness or some variability. So the idea is to study each of the steps, or each of the process of the model, and understand how it behaves on real life, and design some statistic distributions that we use to use on the simulation. So when we talk about randomness, it's not something totally random. Actually, we try to replicate the behavior of specific phenomena in the simulation model through this kind of distribution. This is a triangular distribution. It's just one of the several kind of statistic distribution. But what we do is to pick the model pick for each run of the simulation. It pick one number inside this this distribution according to the probability of it to happen, and it combines different inputs over the whole model, so we get always a different output. So the idea at the end of the analysis is to have the whole range of possible results that your operation will deliver, considering since the worst case scenarios to the best case scenarios and everything in the middle. So at the end of the simulation, you won't have you will not have a single result, but you have a range of results, and the probability of each of these results to happen in the real life. So that's the difference, the main difference between the approaches, the regular deterministic approach and the simulation approach. So simply relying on mathematical averages or static information introduce these blind spots, because flat means or static numbers hide this compounding effect of operational peaks. So when you have several small process on your model, and each of these small process can deliver a different result, the effect that of this the accumulated effect of this variability throughout the model brings the different results that you have on the final result of the model. So, for example, let's talk about a real life example on a port terminal. You can have a specific year with where the weather was great all the time. Your equipment was working well. The maintenance was great. The crane operator was happy and was working with was very productive. So probably you're going to have a great year in these conditions. But you have the opposite. You have a year of El Nino. The weather conditions are terrible. The port are facing constant meteosonographic problems. The equipments are old and are breaking down all the time. The operator is not happy. It's getting it worse. It's not focusing on the operation, so everything goes wrong. So when you add up all this variability in each of the several steps of a process, you can get very different results. So this is what you get at the end of a simulation. Statistic distribution of the results. So usually you have a mean, but you have a range of results that can happen with some probability. So you know that with 95% of the time, your result will be between 2 and 35, whatever number is here. It's just an image, but you have this answer. You don't have a static number. You have a range of results that can be used to analyze the risks of your investment. So the idea here is when you get a scenario where everything goes wrong and you get a bad result, how does affect your financial model? Can you support this kind of a condition for a certain amount of years, or this is going to break the business? So are you willing to get this kind of risk? Can you support this kind of risk for a certain amount of time, or is unacceptable? So this is the difference between a static approach from a statistical approach. So you get, actually, you don't get a result, you get a risk analysis of a risk profile of the results. Regarding port terminal, usually there are several kind of simulations techniques. Usually we use the discrete event simulation for port terminals and for the port industry and for infrastructure in general. And what is discrete event simulation? It is a A traditional model look at time as a continuous flat line. So each event of the model will happen in a certain time. The discrete event simulation, it jumps from one event to the next. So, for example, if you have something happening now, and the next event will happen just in 2 hours, the discrete event simulation that jumps these 2 hours for the next event. So it doesn't take the 2 hours waiting for the next event to happen. So it keeps simulating. So it jumps from one event to another. This is a mathematical approach. It's algorithm stuff. So the benefit of this kind of approach is that it saves time. So let's say if you have a simulation of operation that run just for one shift on a day, it doesn't run like 24/7. So the simulation will not wait the whole night to run the next event. So if the algorithm understand that there is nothing between the last event and the next, it jumps this time and goes directly to the next event. And the mechanics of the simulation is based on these three kind of entities. You have the entity, the thing that is going through the processes. So it can be a ship, a truck, a container, a cargo, a person, whatever. You have the activities, so the processes that act on the entities. So it can be a gate, can be a crane moving a container from one place to another. It can be on a industry, can be a machine that is processing some kind of material. So whatever activity, we model that, and you have the queues. The queues are the storages or the waiting points that come before any activity. And so whenever one activity is being used or is being full, you form a queue before the activity, and you can see the bottlenecks happening throughout the models. So basically, we design the simulation model using these three elements, and of course, it's much more complicated than that. But basically, a simulation model considers these three elements: the entities, which are the ones that are being processed, the activities that they are processes, the entities, and the queues that there are waiting points out through the system. So here is a small representation of a simulation for a berth terminal. So you have the vessel arrival, which is an activity. The tug allocation, this is a resource or an entity. The berth assignment, also it's an activity. The crane operation and the yard stacking. So you have the activities and you have the cargo going through all these activities, and between the activities, you probably will have some kind of queue, some kind of line when the crane is being used, so another cargo has to wait for the crane to be free, so you have the queue formation between the activities. So this is the basic structure of a simulation model. And this, I already talked about it. It's the kind of result that you get. So instead of getting a fixed absolute output, you get a probability distribution of the results that you get over a certain time period that you are simulating. So the idea here is when you get the model ready, we run several runs, called run, and for each run, the algorithm picks input for each of the processes of the model. So you can have like ships arriving at the port on with time time between ships varying from 1 hour to 24 hours, for example. So the model will pick one of these possibilities, can be 1, can be 24, can be anything between, and we'll run one time. So you do that several times, like you do that 30 times, 100 times, 1,000 times, depending on the complexity of the model. You might need more runs to get a statistic representative result. But at the end of the simulation, you get this kind of result. You have a distribution, statistic distribution of the results. So you can say that with some kind of certain, like 25, 99, 95% or 90% of certain, you get the results between these two results here. So you can do the risk analysis on how eager you are to go through the risk to get bad results for some years or whatever. So this is the kind of result that we get. And also one thing that I see happening a lot is that people, I don't like to use simulation to get absolute values. So when we are talking about like port capacity, this is a classic model that we do all the time. Usually the client wants to know if the terminal will be able to handle X amount of cargo on a specific year. But I don't like to work with absolute values because, as I said, the model is a simplification. So it has some kind of error inside of the result. So usually I like to talk uh, about an interval. So you don't say that the like a iron ore terminal will move 20 million tons per year. You say that will move like between 17 to 23, depending on several conditions. But on the top of that, I think the main value of a simulation is to understanding the behavior of the terminal if something happens. So I don't focus much on the number. I focus much more on the impact that change on some kind of assumption, some kind of condition will bring to the result. So if I change the size of the ships that are coming to the terminal, my capacity will shift from an average of 20 million to 25 million tons per year. So the important for me is not the additional 5 ton that you get with this change of assumption, but the 25% or 20 something percent that you get of capacity increase if you change the size of the ship. So changing the size of the ship is an assumption that will bring impact to the model. So I focus much more on the behavior of the system or the consequences of changing some assumptions that on the absolute value of that change. So now I know that if I increase the capacity of the ships, I'll get more capacity. So this is the information that I take out of a simulation, not the number itself. Of course, the number, if the model is it's a good model, the number will be representative, but it's not going to be very precise. Never is going to be very precise. And this is a common error I see a lot in the market. When designing a simulation model, we have to be careful with a lot of things, of course, but with these main 3 types of errors that happens a lot. The first, what we call the type 1 error, is rejecting a simulation model that is correct. Usually, as I see a lot of people trying to get the model to answer the questions the way you want. So you use the model to validate your assumptions. So if I'm building a port terminal and I expect it to to move 20 million tons a year of iron ore, and my model is for some reason telling me that that specific project will reach like 15 million tons a year, not the 20 that was expected. I see a lot of analysts changing assumptions to reach the 20 million and giving the answer that the client wants. So this is what we call type 1 error. Sometimes your model is correct and your assumption is wrong, and you try to adjust the model to give the answer that you want, not the real answer. Of course, to bring this kind of conflict to the analysis, you have to be very sure that your model is reliable. And this brings the expertise of the person who is modeling, the knowledge of the operation and everything. But when you are sure that your model represents the reality, you cannot accept what to use the model to validate a wrong assumption. As we said, sometimes we perpetuate mistakes over and over because we use magic numbers that the market accepts, but not sometimes they are not real or not realistic. Sometimes specifically for that project, sometimes they are perpetual mistakes that are being used by the market. The second type of error is the type 2 error is accepting a model without validating it. And we see a lot of that too. People just build a nice model, beautiful with the 3D graphics, which seems to be working fine, but it was not properly validated. So the results you get are not reliable. This is the classic garbage in, garbage out. So again, to get a reliable model requires understanding of the modeling itself, understanding of the operation. So it's not easy, and it's a trap that I see a lot of people falling in because they do the model, they build a beautiful model, seems to be working, but when you start to testing the hypothesis, the results you get are not real, and you take wrong decisions based on that. And the third type of error is the spending a lot of time solving the wrong problem. So it brings us back to that a problem formulation step at the beginning of the process that has to be very well developed, so you don't spend much time building this nice model that will not answer or will not bring the problems that your operation will have because you didn't define the questions or the problems that you wanted to address in a proper way. So here I try. I'll bring some kind of solutions that we develop using simulation analysis. Basically, this is a classic analysis that we do. It's capacity balancing. So we see a lot of people calculating a port capacity based on the berth key. The berth, or usually the berth is the more scarce resource, the more expensive. So people calculate the capacity of the berth and forget the rest. And on a real life, port terminal is a complex interdependent operation. To have these three main elements: the berth, the landside gate, the gate in and gate out, and the stockyard. So we do a lot of capacity balancing. We analyze the capacity of the berth, and we check if the other two elements can support the expected capacity, or if you need more investment, or the other way around. You invest a lot on the stacking yard, but you don't have berth capacity to handle all that capacity, so you're wasting money on the stack yard that's not never going to be used. So we do a lot of these capacity balancing projects. And we also use simulation to evaluate the financial risk of some operations. I did a simulation like 20 something years ago with just spreadsheets, not using any kind of sophisticated tool. We were designing, I used to work on a third-party logistic operator, and we were designing a multimodal operation that involved cabotage, rail transport, and road transport of containers. So we were taking a container with some kind of chemical product from one factory in the northeast of Brazil to another factory of the same client in the southeast of Brazil. And they were doing that on the road. It was like I don't know, 3,000 kilometers trip. And they had a lot of issues with that. The cost of the operation was huge, and the reliability was low because they had to keep the cargo flowing all the time, and they had problems on the trips, and so it was a very complicated operation. But they couldn't establish a multimodal solution because of the merge of the containers. That was the main problem, because the cabotage system in Brazil is not very regular, so you don't have calls on every port or with very they're not very regular, so you have some variability. Sometimes it takes 1 week between calls, sometimes more, sometimes less, and the same with the rail transportation at that time. So the problem for the client was how much he was going to pay, because he knew that you were not going to be able to deliver the empty containers back to the ship owner on the 21 days that they had. So they had to calculate the cost of the mortgage. So we did this simulation, and we could answer the probability of the cost of each container regarding the mortgage cost. So we could budget the operation and show them that even with the merge, the multimodal operation would be cheaper and more reliable than the road operation. So sometimes you can use simulation not to answer specific operational issues, operational questions, but to analyze the financial risk of operation, or to budget some kind of cost that's going to be very variable according to the conditions of the operation.
André, we have 5 minutes to the meeting, so if you want to start wrapping up.
Okay. I brought 3 cases. This one was a liquid bulk transshipment terminal. We did a simulation. They wanted to understand what were the main variables that would affect their capacity, so they could negotiate with the authorities some more flexible conditions to operate. So we did this model that was very flexible. They could change the assumptions. They could add berth. They could change the operation. It was ship-to-ship crude oil transfer. They could study a short-to-ship operation. So it was a very flexible model. This was a solid bulk iron ore terminal that we were evaluating, and they had the main operation, which was iron ore, and they had other minerals. And this was a due diligence. The client wants to invest in this terminal, and he wanted to validate the capacity, because of course the capacity would affect the valuation of the business. and they wanted to know how the other minerals like coal and other minerals that they were operating affected the business model, and if they phase out these other operations, how that would affect the capacity of the terminal overall. So we built all this simulation model. And this is a third case study that it's a more operational issue. The client wants he knew the result, but he wants to have an analysis to prove that the operation it was a container terminal, and he wanted to prove that he needed a stacking area close to the berth and not far away from the berth. So he was trying to convince the investor to get more area, to get more yards. So he wanted to show the impact on the operation from taking the stacking area away from the berth. So we did an operational simulation for that. And to conclude, so simulation is a very powerful tool, but it's a very dangerous tool too when it's used without technical rigor, and when it's bad used. So it can, the same way it can bring good information, good results, good analysis, it can bring you bad information, and sometimes people rely on these results because it's a simulation, so it's sophisticated, it's fancy, it's graphical. But as I said, garbage in, garbage out, so it has to be used with a lot of care. And one thing that I learned over the years is that the software, the technical side of the simulation is not the most important. The graphical side, the software that you're using, the tool, the simulation is much more than that. It's the knowledge, the operational knowledge. It's your capability of understanding how a port terminal works, what is relevant, what is irrelevant, and your ability to analyze the results, analyze the input data that you have. So usually I say that the simulation is 20% software and 80% the humanware, the human factor, and knowing what you're doing both on the coding side of the thing, all the technical side of the thing, but also knowing the operation, knowing what is behind the computational solution. So that's it. I think I took a little more time than I was expected, right?
It's all good. Thank you so much, André. It was right on time, actually. Well, I wanted to open the floor for at least one question. If anyone would like to ask André one question, and then we wrap up this meeting.
Julia, I actually don't
Go
have
ahead.
any question, but just congratulate André for the presentation. Port for
Thank
setting
you.
this webinar. Is a very interesting moment we have in Brazil with a lot of concessions and projects, big scale concessions and projects coming out. So it's I know Graf, Rodrigo Paiva, and it's a very expertise company. So it was good to know more in details, André. And this presentation is going to be shared.
Yes, we can make the presentation available if André would like so.
Sure,
Okay.
sure, of
For
course.
sure.
Okay, I'll share with my colleagues here, and we'll certainly have some other points, and of course I'll reach out to you and through your portal directly and continue this the analysis of this presentation.
it's a very powerful tool. We've been using a lot, and it really brings another perspective for the investment analysis.
Yes,
If it's
and
well
the
used.
first point of your presentation about the trap of the master plan, this is very interesting because we receive
Yeah.
very fixed rates, and it's hard public concessions to discuss and to review, but it's the model that you have, and then the right thing to do is like do an analysis, data driven, with the human wear factor, of course, but do a thorough analysis and try to prepare yourself.
Yeah, it's important to confront the assumptions that we use historical information from old studies, and we are always replicating that. So it's important to confront that, and sometimes the results are very surprising.
Yes, indeed. Congratulations.
Thank you.
Well, since we are over 3 minutes of the expected time, we are going to wrap up another webinar session. So thank you once again, André, for sharing your expertise
pleasure.
and practical experience with us today. And thank you to everyone who joined us from different parts of the world. Your participation is what makes this international community so valuable. So as a reminder, today's webinar recording will be available soon at the official eAports YouTube channel. We'll also make available André's presentation, Graf Infra's presentation. And we also invite you to follow eAports on LinkedIn and Instagram, where we share regularly our webinars, international initiatives, member highlights, industry news, and also upcoming events. So thank you once again for being with us today. Together, we are shaping the future of ports. eAports, connecting ports, navigating the future. Have a wonderful rest of the week to everyone.
Thank you. Bye-bye.
Thank you, Julia. Bye-bye.
Thank you all.